Thank you. Hi, so I'm Matt Tancik. I work at Luma AI, and in today's talk, I want to explain what Nerfs are, what they can be used for, and how Luma plays into the picture. So what you see in the background there, that is an example of a Nerf. I captured this the other day, took about 30 seconds. So if we want to capture the world around us, what do? We all have cell phones in our pockets. We can pull them out. They have cameras. We take a photo. If we think 300 years ago, what would we do if we wanted to capture a moment? Well, you would have to go to art school, train for 10 years, buy all the paints, do all the technical skills, and then maybe you can create a nice painting. It's a very time-consuming, laborious process, and in many cases, you just want to replicate the world around you. And so if you look at 3D these days, we're doing a lot of that, whether it's for gaming, for simulation, having robots travel through scenes, if we want to document the world around us, or if we want to use it for VFX applications. In many of these cases, all we care about is creating a photorealistic version of the world around us. And so a lot of this starts to look like the painting of 200 or 300 years ago, where there's a lot of manual effort taken that's very tedious and time-consuming. So what if we can create something similar to a camera, but for 3D? How do we actually accomplish that goal? And this is one of the goals of Nerfs. Now, the first thing we have to figure out is what we actually want to represent. For an image, we represent it with pixels of different colors. Now, if we want to represent the 3D world around us, it's a little bit more complicated. What we really want to be able to do is enter the scene, and at any point in the scene, if we look in any direction, we want it to produce the right color. And what we call this is the planoptic function. So our goal is to represent this thing called the planoptic function. We have to start with something, and it turns out that hardware to capture the planoptic function is not easy to come by. So what we're going to use instead are photos. So we want some way to create this planoptic function given a set of photos. And this is what the Nerf is going to be. So now that we know what we want to create, how do we actually represent this type of format? Well, we can start considering some possible representations. Maybe we use something like a voxel grid. So in a voxel grid, it's a 3D space where every point is either occupied or not occupied. We've got the x dimension, y dimension, and z dimension. But in a planoptic function, it's a little bit more complicated because what we really care about is the color if we look at it from a different perspective. So there's two additional dimensions that are added. One for like the theta and phi, basically describing the orientation that you're looking at this point in space. So what we're representing is this 5D function. And the 5D function has a few issues. And it's of resolution. If I wanted a high resolution representation of my scene, it's going to use a lot of memory. If I have, say, 1,000 pixel resolution, now you've got 1,000 to the 5th power. It's too expensive to represent on most computers. And so we need to come up with tricks to make this more compact so that we can represent these high dimensional representations. And so we're going to play with one of these tricks in Nerf, and that's to use something called an implicit function. So if you remember back from maybe geometry class, you can represent shapes and objects with simple equations. I can represent a circle with just x squared plus y squared equals 1. Alternatively, I can represent a sphere with this equation, x squared plus y squared plus z squared equals 1. And what's cool about this is it's sort of infinite resolution. I can keep zooming in forever, and it perfectly describes the object that I'm interested in. Now, this is a very simple object, and it's described by a simple equation. How do I represent a more complex object? I can start combining multiple equations together to get these more complex objects. So for example, here's a rabbit that someone figured out a few equations to create this drawing. Now, a human was able to do it in this case, but if I want to represent, say, this conference room right here with every single person in it, how would I actually come up with that equation? That's something that no human would really be able to do. And so for that, we're going to rely on the advances in machine learning to do that task for us. Turns out that a lot of these machine learning methods are effectively just a whole bunch of equations that are trained to modify little by little until they match the output that you're actually interested in. And so we're going to use something called a neural network, MLP, multi-layer perceptron, and we're going to call these coordinate-based neural networks. And the idea here is it's a network that takes in some input coordinate and then predicts some value at that point in space. So for example, if I wanted to represent a 3D object, I could take in the spatial location, the XYZ location, and have it predict, is there something there or not? I can then query this network at different locations to recover the object. And depending on the resolution and the density that I query it, I can get different resolution outputs. And what's cool here is now the resolution is no longer tied to storing data directly in this explicit representation, but rather this model is now stored in the neural network weights. And you can use this trick to represent all sorts of things. It could represent if something is there or not. It can represent what color that point in space is, maybe how far away that point in space is to the surface of an object. And the representation we're interested in is representing the planoptic function. So in that case, we're going to go back to wanting to take in the spatial location, but then also take in what direction am I looking at that point in space. And we're going to train this network to predict the color of that point in space and whether there's anything there. So basically the density of that location. So we have this network now. How do we actually use it in practice? Say we have a bunch of images of a scene. We can consider one of these images and consider specifically a pixel on one of these images. If we shoot a camera ray through this pixel, we're going to take these samples along this ray. For each of these samples, they have an XYZ spatial location, and then we know the angle because of the angle we're looking at the sample, and we're going to feed that into this network that I just described, and we're going to have that predict the color and the density for that point in space. So we can do this for all the points along this camera ray, and then combine them together using something called volumetric rendering to get a single color for that camera ray. We can compare that to the actual image that we captured color, and any difference there can be used as a signal to update this network so that we can effectively train this neural network to represent the scene we're interested in. And so this trick works rather well in practice. So from anywhere from 20 to 100 images, you can create these photorealistic outputs where you can move the camera around in the scene. And since we're explicitly modeling the fact that we know what direction the camera ray is going and how the materials react to that, we can model things like specularities in the table or the screen in this particular example. And since we're also modeling how much stuff there is in every point in space, we know the 3D geometry, which can be used for compositing multiple of these Nerfs together or compositing in other 3D assets. So the method that I described works, but it's not perfect. It has many, many limitations. For example, it's extremely slow. You can't represent a very large scene. It might not handle well if some of the images that you give it to train with have different exposures. So the baseline method is not super great. But conveniently, there's been a lot of work that has tried to advance this in the past few years to account for many of these limitations. For example, it turns out you can speed things up a lot by combining these voxel grids with these implicit functions that I was describing earlier. Now, this list is rather overwhelming. And if you just want to use Nerfs, you don't really care about this. You just want the latest and greatest. And for that reason, we have Luma, with the goal of making this kind of technology as accessible as possible for anyone who wants to create these kinds of Nerfs with just an app on your phone. So if you have an iPhone, you can download the app, capture a scene. Once you have this scene, it will be trained to produce a Nerf that you can then create camera paths with, render images. You can export them as meshes to put into video games. You can also just export directly into Nerfs into Unreal Engine for downstream applications. And if you don't want to use the camera app, you can upload video data or image data directly to our website so that you can create these crazy captures as if you're flying in drones, from very large scale to also very small scale, intricate captures where traditional photogrammetry would really struggle, particularly on things with like reflections or other more complicated material effects. And so it's worth noting that this is not just legacy traditional photogrammetry, because we are able to model the fact that colors look different from different angles. So in this example, we can see that the car properly reflects the light as you move around in the scene. And so this sort of brings a new paradigm to how you might go about capturing a movie, where in the past, a lot of time and effort went into pre-planning for exactly how to create camera paths and motions. And then when you're actually on set, you have to make sure that you capture it what you want, because you can't go back, or at least not easily go back and remap how your camera moved through the scene. However, with these Nerfs, once you've captured the scene, you have a 3D representation that you can create arbitrary camera paths after the fact. So if I told someone to just, I want a video of moving straight through a scene, you'd hope that they would do something like the left here. But if you have some crazy camera operator and they do something like on the right, you'd think you're completely out of luck. But with Nerf, if anything, the one on the right is actually a better representation of the scene, because you see it from more angles, and then you can go after the fact and create a Nerf and render it whatever camera path you want. And it's very accessible now. All you need is a phone. So I went on a hike a few weeks ago, and I just took my phone with me, no fancy camera equipment, took a few photos. I didn't know what I wanted to do with it. Last night, I put it in our web editor and created this camera path and was able to create these animations that traditionally would be rather difficult, especially after the fact. I could even go in and change the camera settings, like the focal length, to create more cinematic shots, which definitely would not be possible with just your standard iPhone. We have ways to even make shooting and creating camera paths even easier. So in the mobile app, similar to what I was just showing, you can create these key points and create a camera path. But alternatively, what I think is more fun is you can go into this AR mode where you treat the phone as the camera. So you have the 3D model and you can walk around as if you were shooting with a normal camera and create your own camera paths that way, motion stabilize it, and create things that would have been very difficult otherwise. For people who want a bit more control, we have the ability to export these Luma files directly into Unreal, where they will be rendered as actual Nerfs. So it's not some intermediate representation. And once they're in these Unity files, you can do whatever you want with them, really. We have the ability to export at different levels of quality so that you can trade off between performance if you need really fast, high rate reaction versus if you really want the high quality details. And so with things like that, we can then use LED walls like the one behind me to do VFX production, LED screens tied through Unreal for virtual production. And these Nerfs have gotten to the point where, in many cases, these are all Nerfs. And once you add camera paths that have camera shake on them, it can be hard to distinguish them from just raw input camera or output camera data. So people in industry have started using Luma already. Here's I'll show a few examples. Here's one of a McDonald's commercial. Or a car commercial. And you can start intertwining these with actual live or real video outputs so that you can use Luma or Nerfs for these impossible camera shots and intertwine them. Just a couple of weeks ago, here's another example where a music video by Zayn already has 10 million views, made extensive use of Nerfs to create these shots that would have been extremely difficult to capture. And all these shots were taken over the course of a day with very little prep compared to a normal camera shoot, because a lot of it could be done after the fact. And after all, these are just graphics elements like anything else. So you could then take them, put them in video games, treat them as any other graphical element, from anything you scan. And so that summarizes my talk. Thank you.
Alrighty, who's got a question out there? Let's see a
Hello.
hand. All right.
Is it easy to extract the actual camera data for like After Effects or Nuke?
From the original images, or?
So like if I make a keyframe camera,
Ah,
can I then get that camera data into a compositing platform?
Yep.
So I can add things.
Yep.
Cool. All right, who's got a Phil Squires?
What are your rules for capturing the original stills to make it work best?
So there's a lot of tricks. It's at this point more of an art than a science, but doing things like reducing as much motion blur as possible, trying to get the highest diversity of images. So taking it from as many random angles as you can helps improve the reconstructions. Other things don't actually matter, so actually having like noise in your images isn't a big problem. It's motion blur and these other artifacts that are bigger issues.
All right, another question. All right, Alex.
Hi, does it have any indication of a mesh associated with the 3D model? I saw that on one of those shots, the balls were bouncing around on the floor. What's the geometry associated with the Nerf?
Yeah, that's a good question. You can extract meshes from these models, but you often lose a little bit of quality. So then you can play these tricks where you extract a mesh, but then you also have the Nerf rendering to get the best of both worlds.
All right, you want to come a little closer because we're going to get reverb off.
Well, what kind of features are you working on adding or improving?
So generally, we're trying to make these as high quality as possible. So we have a number of features in the line to just improve the visual fidelity, and then to make it as accessible as we can. So one big issue with these types of models is if you don't capture it, we can't render it. If you capture a scene but you forget that corner of the room, at the moment you're out of luck, but that's one area that we're investing in trying to improve.
All right, we're going to go to Rob Sloan next because we got to get a question out of him.
So one of the papers that came out this year was from INRIA, I think. It was the 3D Gaussian splatting. How does that fit as a new layer on top of the current Nerf build-out?
Yeah, so these are all representing this idea of a radiance field. So some field of stuff that looks different from different angles. The actual representation is something that there's been a lot of research in. The paper you were describing is sort of one of the latest and greatest in terms of speed and quality. And I imagine that will continue to evolve over time.
Awesome, thanks, Rob. All right, one more question. All right, Nathan.
Hi, just wondering, how do you handle relightability? So like say you capture a scene, you bring it into Unreal Engine. Can you handle relightability with additional objects that are brought into that scene?
So to a limited extent. You can do things like cast light onto it, colored light, things like that. But if the scene you capture has shadows to begin with, you can't remove those shadows because they are baked into the underlying representation. Now, this is an area of very active research that is trying to essentially decompose these even further so that you have more control over relighting.
All right, awesome. Thank you so much, Matt. Really appreciate it. Fantastic talk.
Thanks.